Space is critically important to visualizations. It's the thing that people can judge most accurately. That's where things are positioned in a visualization. Thus, when we have data, choosing where to position it and how people will perceive it in space is one of the most important decisions we have to make for them to interpret the data that they're interacting with. So I want to talk today about a few different kinds of spatial visualization. We're going to start with maps, which actually have a spatial component, but then we're going to move on to more standard kind of charts and visualizations and talk about how we can maximize the space that's being used. But starting with maps, these are symbolic depictions of relationships between elements in space. We often think about them geographically, that there are geographic places and a map is going to show us their relationship to one another. These are commonly done as static geographic maps. These are super common. Obviously, you have worked with these both printed and online. But there's all kinds of maps that are out there to show information that sometimes doesn't include any geographic information, or if it does, that can be skewed. So the first law of geography is that everything's related to everything else, but near things are more related than distant things, which sounds a little silly, but it's actually core of a lot of visualization. That when you see things close together visually, you expect that they are more tightly related than things that are far apart. And you want to keep that in mind when you're laying out space, because it can be deceiving how closely related things are or how important things are when their spatial makeup does not necessarily reflect what's going on in the data underneath. For example, think about a map like this. You see these all the time. So here we're looking at the state of Indiana divided, I believe, into counties, but voting sections. Each section is colored based on who they voted for in the 2008 presidential election. So the brighter red it is, the more Republican they voted. The brighter blue, the more Democrat they voted. These are really commonly used. I'm sure you've seen these for elections, but they're kind of problematic. They are using space because they have the geographic space of the individual counties, but that space does not necessarily tell us everything about the data. What we often see in these maps is that there are big geographic spaces with very few people in them. And so we can get maps that often, what happens politically is that they look extremely red. The whole middle chunk of the country looks red because it does vote very Republican. And so you wonder, how can we get a Democrat winning the election when there's this huge chunk of the country that votes intensely Republican? And that's because the size of those red states is shown according to their geographic space, which does not reflect their votes. There's very few people living in those states compared to the coasts, and so the actual number of votes is quite small. Thus, we get a little bit misled with the way that space is being used, because while it is accurately showing us geography, it's not showing us votes. Though the spaces are color-coded by votes, it's not showing us how many are there. There have been attempts to correct this. So this is a map of the United States, but each district is sized based on its population. And so we can see, for example, Chicago, right here in the center, really big. It's a pretty small county, but in terms of geographic space, but it's huge in terms of population. We have the same thing for major cities on the East Coast. Florida looks much bigger, along with San Francisco and Los Angeles taking up a lot of space. That big red swath of the country that always looks so giant is actually really compressed in here because there's not very many people that live there. And so most of those counties smush down to very small spaces, and the large urban areas take up a lot more space. Now, this is obviously completely not representative of the geography of the country, but it's very representative of the voting population, which is what we're interested in when we're showing how much do people vote one way. So it just indicates ways that we can control the physical space that we're showing to more accurately represent the data. Now, people don't like graphs like this, right? This is very jarring to look at when you're used to the map of the US looking one way. But it's important to think about, does your visualization accurately reflect what you're trying to show? And if you're trying to show how many people voted for a particular party, but you're greatly outsizing certain spaces by showing their geography instead of their population, you're not necessarily communicating the data effectively, and this could be a way to change that. Talking about substrate, this is basically, we're going to talk about scatter plots and line graphs and what scales do we show them in, what scales do we use for our axes. You can show data in a lot of different ways. This is from How to Lie with Statistics. It is the same data on both sides, but the scales are quite different. So the one on the left starts at just under 19 million and goes up to 20 million, so it looks like you have a really sharp increase. Exactly the same data here that starts at 0. Which one of these is correct? The answer is it depends what you're trying to do. I am a super strong advocate of always starting your y-axis at 0, which is a graph like this. Now that does not maximize what you're able to see in terms of variation in this graph, but it most accurately conveys what's going on with the data. You don't want to claim a sharp jump when there isn't one, and people often use non-zeroed y-axes to lie about things. So that said, if we're just talking about allowing people to visually explore changes in their data, there are ways that we can adjust the axes, but I want to emphasize super strongly that there's a different task between allowing people to explore the data and ask questions and communicating the data accurately. So don't go thinking that you can just start all of your y-axes wherever you want. You shouldn't be doing that. If you're communicating data, you need to think very hard about if you're misleading people into thinking that something's more significant than it is by manipulating your axis. But if we want to talk about visualizing and allowing people, if our task is maximizing their perception of trends in the data and discerning the angles of lines, the best thing that you want to do is get them roughly to about a 45-degree angle. So that's basically going directly from one corner to the next. If you can make that kind of the peak angle that people can see, it makes it easier for them to actually see what's going on in the data. If it's too shallow, like the middle option here, it makes it hard for them to perceive those changes. And if it's too steep, it makes it similarly hard, just in the opposite direction. So if you can orient it so your data goes on those 45-degree angles, it allows them to see the difference between those lines more clearly. Another way that you can screw up the way people perceive the data is if you have outliers. So this data here has one big outlier up here. Everything else looks really flat. Notice the y-axis here, it goes up to 150 as our highest label, and this is a little bit above that. So this all looks about the same because we've got this big outlier, but if we take that out, this is exactly the same data. Now the y-axis only goes up to 30, and suddenly we see that there's actually a lot of variation in that data down there. So you want to think about, what do you do if you have an outlier like that? And there are some techniques that you can use if you have a lot of space that's just kind of empty but screwing up the rest of your visualization. And we'll look at those in a second. So one way that you can do that is with a scale break. So take a look at the x-axis down here. We have 0, 100, 200, and then where 300 would be, we've got a long break. We jump up to 400, and notice that this scale is different, 400, 800, 1200. So it allows us to see more of a pattern in the data, but it can be a little misleading to think that we're just going on a straight line here. We actually have kind of made a virtual log scale here because these are on a much different level, right? These dots are many more hundreds apart than ones of the same distance over here. It does allow people to see more data, but it is deceiving and requires them to really pay more attention. Again, if someone's trying to explore the data and they're asking questions, they're going to be more aware of this. If you're just trying to communicate data to people, this can be really confusing. We also have a break over here. So notice our x-axis goes 10, 20, 30, and then there's a break. It goes up to 100 and then 200, so our scale changes over here. It makes for a really nice pattern in this data, but it's misleading for anyone to think that that pattern is linear like it's displayed because there's a big break here. What actually would happen is that there's this dot, and very far right off the end of the screen would be the next dot, and very far past that would be the one afterwards. So our scale actually levels out here, though that's not shown. Now, this allows people, again, to see differences in the data before the break that they wouldn't be able to see if it wasn't there, but it's a little bit misleading in terms of the patterns that are visually shown. So you have to be really careful when you're doing this. One way that you may be able to do it more effectively is to use logarithmic scales. So we have a linear scale up here in the top graph, and you can see that we've got our years broken down by fives, and our y-axis is by tens. Here we have the same x-axis, but our y-axis is still by tens, but they're not spaced evenly. This is a logarithmic scale. So basically, as you get closer to 100, things get closer together. And what that allows us to see is basically data when you have a curve like this. We call this a power law distribution, or basically a logarithmic scale or an exponential scale. You put it in log scale and it looks more linear. A lot of data has this pattern where everything kind of just smushes up on one end. You get this sharp curve, and it's hard to kind of see what's going on. If you put it on a log scale, you get something that looks more like that 45-degree angle that we talked about. It looks a little bit more linear, and so you can perceive differences in it. And unlike the other options that we were looking at, like splitting the scale or putting a break in, this is less misleading. People still need to know that they're looking at a log scale, but it typically is shown with your bars like this. It's labeled as a logarithmic scale, and so it's much more straightforward about the way the data is being manipulated in order to make it visible like this. You also want to think about using white space. These two graphs are of the same data, but you can see the axes. This one goes from 0 to 10 on both the x and y. This one goes from 0 to 5. So we're basically zoomed in on the data more here. It looks really closely clumped together when we're zoomed out, and it looks much more spread out when we're zoomed in. So you need to think about which scale do you want to use to accurately communicate your data. This helps us see more of the pattern, but it makes our data look a little bit less reliable than it does over here when it's all clumped together. And finally, let's talk about navigating through space. So we've talked about maps, we've talked about substrates, now we want to talk about navigation. It's hard to see all of your data on one screen because there's lots of variables. Sometimes you just have to use more space than will reasonably fit on one screen. This is a common problem. How do we deal with it? The standard approach is that you have a multi-scale visual display, which means that you start at one scale and you can zoom in or zoom out, and you can pan to go across. So just like you're used to doing with a map, if you search for something on Google Maps, you see it in one scale, you can zoom in and zoom out. You can also just drag it around and pan. So that's what we're talking about, basically moving around on the map, zooming in and zooming out. Just a couple cool, interesting examples of this. This is one called Deep Zoom, actually on the NASA website. So we have a little tiger here, but if you were to zoom in on it, we can see a little bit like, oh, there's some dots in there. And if we zoom in a little bit further, we actually see each pixel of this is made up of another graphic. And so you can keep zooming in and find all of those graphics. So not especially useful for gaining visualization insight from an InfoVis perspective, but an interesting application of how you can fit a whole bunch of images into one space and use zooming to make some discoveries. Zoomable user interfaces were a really popular research topic about the turn of the millennium. A lot of work was done here by Ben Peterson at the University of Maryland. These were called ZUIs, Zoomable User Interfaces. And it's interesting that on one hand, these aren't focused on in the research space anymore. At the same time, they've made it into a lot of commercial products. So obviously, we're used to having zoomable user interfaces on maps. They did not have smooth animated zooming before. You all probably are fortunate enough to not ever remember the world before Google Maps that are really nice to use. But there were like MapQuest maps before, and you would get a view, and if you wanted to zoom in, you could, and there was a button, but it would just load up a new screen. So it wouldn't actually animate on that zoom. You would just see it at one scale, and then if you zoomed in, the page would reload at the new zoomed in scale. And so it could be really disorienting. Zoomable user interfaces added this element of animation to go from one zoom level to another and to allow you to zoom potentially as deep as you want. There are a bunch of tools that they created to do this. There was some for browsing photos. iPhoto now on Apple, the photo app has this on the desktop version. There was a plugin for PowerPoint that allowed you to do presentations that zoomed. This is essentially what's in Prezi now if you've used that to make presentations. So a lot of it's made it into commercial spaces, though it hasn't taken over the world the way it was originally envisioned, I think. Another challenge that happens when you can zoom in and out is that content moves off screen. So if you zoom in, you're only looking at what's on the screen, and then there's stuff around outside the screen, but you may want to be aware of that. So you want to maintain your context for what's off screen, but you don't want that to be distracting from what you're looking at on screen. So how do we handle that? How do we maintain indicators about what's off screen while not distracting from what's on the screen? One interesting technique that was used, again, way back around 2003 was something called the halo, which was basically if we had things that were off screen, so imagine what we have over here on the right with little icons that are off screen, they get a halo around them, and that halo is big enough that it touches the edge of the screen. So things that are really close to the edge have small rings around them, things that are very far away have big rings, and they're positioned just so they arc into the screen. What that does is when the user can see them, they see the edges of these halos, and by basically the diameter of the circle, which you can tell from that arc, you can tell if there's something really close just off screen or if there's something very far off screen because you see the edge of that circle. It's a little more useful visually than something like arrows that tell us distance because I have to interpret those numbers. I actually have to stop and read them, where the arcs that I can see from the circles just kind of show up in parallel. A variation on that is the wedge, where you imagine a triangle that points out to the targets that are off screen, and it has a bottom of the triangle which forms a little wedge shape pointing towards it, and again based on the size of the bottom and the angle that you can see from the edges of that wedge, you can tell what's off screen. These were really useful ideas. They're not especially practiced in industry today. We don't have a ton of examples of this, but they're still useful for knowing because there are ways that little hints of these can make it into all sorts of visualizations that you do, even if it's not your main focus or interaction technique. So just to wrap up, visualizing space, it's super important to do this right because it's one of the things that people perceive most accurately. Whether you're doing that with geographic space, with the layout of a scatter plot or a line graph, or with a space that you need to zoom in and move around on, you want to think carefully about what's going to allow people to perceive and understand the data most effectively and most accurately. Avoid being misleading, allow them to maintain context, and hopefully your use of space will allow your visualizations to be as effective as possible at helping people gain more insight.